Well, as announced last week, we're going to have a special speech by Dr. Thoery. He just got a PhD in IIT in the field of graphene. Well, soon there will be a composites, mainly currently carbon fibers, but soon we're going to have a nano composites. So please welcome Santoshi, and then.
First of all, I'm very thankful to Professor Ha for providing me this opportunity. After this, I have a very humble request to all of you. During the presentation, if you have any conversation problem or English problem or maybe accent problem, then please stop me. We will go step by step. So,
Yeah.
So this is just an introduction about the nano words, nanomaterials. So we are going to just cover the introduction. Even a single slide, if you have any doubt, any query, you can ask. There is, if you have my accent problem, in English problem, speaking problem, communication problem, it will be pleasure if you ask anything. So, as it's mentioned in title, Introduction of Nanomaterials for Mechanical Engineering. We all know that nanomaterials are hugely applicable for the every field of science. It's a slogan, it's a material you can use anywhere. Even a single material can be used in a diverse field. So we are going to cover very introductory, just like class, it's our body. We are not going to just class, just introduction. So, oh, sorry. This is not working. What is that? No, it's just okay. So, our universe, whole universe is full of materials. Everything is material. The building, everywhere, what we are seeing, even light. It's light is also lights contain photon and just quark and everything. So everything is material. So in this class, you have to see the things on the basis of material. Everything is material. So all the materials for the broad spectrum, we can divide in the two categories. Just one, just engineering purpose and food purpose. These are for the civilization. These things are very necessary. It's very introductory and these materials give all the civilization, the modern civilization where we are standing. These are the materials. But interestingly, these materials, the nature provides these materials in form of different wares or in natural forms. It is not as it is we are going to use for the engineering. For example, this is laptop. We are using silicon. Silicon we obtain from the wires, but it is not. So we need a lot of engineering. We need different kind of engineering. Material engineering, chemical engineering, mechanical engineering, nano engineering. So many things is needed. So, but what is the problem? These wires, so we need. There is a different engineering, and in engineering, in science, there is a concept. Suppose this is my pen. If we just going to dissect, the property of the material is not same in the everywhere. So you can very easily understand by this. Suppose this is the same material. I'm showing by the different color. Just you go and divide. The properties here, I'm talking about only just concentrate on physical properties. Here and here is not equal. It's totally different. Maybe sometime it's amazing. You cannot believe. But the property is identical. Here is the same. Here only difference is size. Size means you have to just understand you are going to divide and many times fragmentation. You are getting my point? Sure. So this is the reason we are coming in the nanoscience. If we study the material size in this range, 10 power 7 to 10 power 9, then it is a nanoscience. And this is how you can small the nanomaterials. Our one simple here is a 10 power minus 5 micrometer. But again, 4 times, just 10 power 4 times you have to decrease, 10 power 9 times is the nanomaterials. And interestingly, the concept of nanomaterials is not new. It is Feynman before the 50s who predicted we are just fool working with the bulk materials. The materials are amazingly when go the beyond the very, very limited, very, very minute side. So this is the all credit of the nano word is today going to the Feynman. So next, in our next slide, what is nanomaterial? Now I can, you may be some familiar with the term nanomaterial. So what is the nanomaterial? Any material, anything, this table, this laptop, me, you, everyone, if have the size in 1 to 100 nanometer, then it is a nanomaterial. So the definition of material, a material must have the size from 1 to 100 nanometer. And the science related to these nanomaterials is nanoscience. And the technology related to the technology invented, technology produced due to these materials, we called nanotechnology. So we have to see what is the uniqueness, what is the new in these materials. Suppose this is pen, this is my pen, and if we go in the nano level, what is the difference? So very interestingly, you get new physics, new electronics, very high surface area. We will discuss about the surface area in the next couple of slides. Aggregation and agglomeration properties. For example, this is my hand, both have the different one. In this, we cannot eat, in this by. So this is the just like the example of aggregation and agglomeration. Surface morphology, we have a probably lot of chance for the surface manipulation in the case of nano. We will discuss in the next slide. New solubility. For example, if we have a material not soluble in water, we go in the smaller size in nano size, maybe the same material highly soluble in the water. So we have the same material, but in the different scale, we have different properties. So like the structural formula may be different, new surface properties like the charge, tension, and these things, and hydrophilic and hydrophobic nature. So in this, up to this slide, I think you are all clear the property of the material going toward the from bulk to nano size means micro and then nano and then many mesopros and like that. We are not concerned with this. In the case of nano size, the properties of material change very rapidly and in very significant manner. And these new properties are very exciting for B scientists, B engineers. In the 10 years, maybe our work completely different. So what is the real-time applications? If we see, these are countries contributing toward the nanoscience. This is first in China, in publication, in patent, in even inventions. Second is United States. Third is India, Japan, Iran, Germany, France, South Korea, United States, and Russia. This is the 10 countries, and this is the 10-year scale of the invention and production of the different kind of things in the nanoscience. Interestingly, if you go again, what is the field? What is the different kind of field producing toward the nanoscience? So if you can see here, engineering, it's a very bulk portion of the invention coming from the engineering. So B engineers need much more attention toward the nanomaterials, and they're giving very excited. So again, we going toward the classify the materials, again classification. Then this type classification for the nanomaterial. What type of nanomaterial? So we can easily divide these materials in the 4 category: 3D materials like bulk materials, 2D materials, film and plates, 1D materials like nanofiller, wires, and spheres. And you have to keep in mind the shape. Now the size is just forgot. Now you are in nano world. Now the size is very important. Shape is very important. Suppose you have 2 nanometer material, but if shape is 3-dimensional, shape is two-dimensional and then you maybe have the different properties. So now we have added another point in our definition. The properties of nanomaterial very, very significantly change with the size and shape. So what is the really, what kind of material we produce? How we can produce these materials? So these are the techniques we will discuss. If we take the other classes, we will discuss all these things step by step. Chemical vapor deposition, chemical route, physical vapor deposition, plasma process, self-assembly, and soft litho. But mostly it's very common, the chemical route. For the production of bulk amount, but for the very pure amount, for the electronics use, we have to go for the chemical vapor deposition or the plasma process. These produce very pure. In the chemical view, you can produce very bulk amount easily and cheaply, but they are sometimes contaminated. So this is the real time product of the, this side is shown, these are the real time product in the market. This is the Samsung first flexible mobile, Samsung mobile. It's very costly. They stopped the production. This is the graphene mobile. You can just Google out. This is the flexible. You can just make flex very easily. This is the transparent cell phone. This only 1 or 2 chip. It's a completely transparent. This is produced by the graphene and related materials. This is the nano sensor. We sometimes for the detection purpose and many medical purpose we need nanoscience. And these are many targeted drug delivery in the market. What is the targeted drug delivery? We have to understand. For example, we have pain here. Nowadays, all the traditional medicine we take, just go and in the stomach, start the chemical reaction and come here. So there is a lot of additional side effect. We are just worried, scientists, so this is antibiotic is very side effect. This is very side effect. So now that it's very, it's one of the wonderful fruit of the nanoscience. Nanomaterials are so amazing. You can design a material just so the chemical reaction here. And just kind of stimuli. We are using the sensor in our building. We are in, light is on, we are going off. That kind of, these kind of material also called switch on, switch off materials. These kind of materials also called as intelligent material. We will discuss in our next classes where nanomaterials again can be divided intelligent material and non-intelligent material. Many materials are quite intelligent. They can understand what you want. Even if you just manipulate the things, they can understand. So these are, and the process, the next is coming applications of the nanomaterials, carbon capture. It's a big problem. We are producing carbon dioxide huge amount. So global warming. Now nanomaterials are showing very efficient storage of the carbon system. So if we can easily store, because storage is so many things has been developed. There are so many technologies is there, but they are very costly. They are in not market. The developing countries like China, India can, and even developed countries cannot afford. So nanomaterials are very, very efficient for the carbon capture and environmental protection. If we can able to capture all the carbon dioxide, we can store, we can convert in other form of carbon, and we can use as a polymer, as a film, and like many applications may be possible. For the molecular structure, polymer blend nano composites, which we are going to for the next word maybe, because we cannot produce now new materials. So we discuss in the next slide, supercapacitors, hybrid nanostructure, 3D printings, and smart and intelligent materials. So these are the future. These are future, are the prototype application has been developed till the day. So next, here in this class, we are mostly concerned about the carbon nanomaterials. And in carbon nanomaterials, graphene is amazing. It's known as wonder material. It's a wonder materials, amazing. So we all are very aware about diamond and graphite. Very, very aware. It's for a very long time. And these two material itself in the bulk form have many applications. There is no need to go in nano. These are for the cutting tools and wearing, high thermal conductivity, stop the electrical insulation, semiconductors, optical component, high quality sounds devices, this kind, and for the thermal resistance and low fabrication, for the friction and self lubrication, high electric conductivity. So these itself, diamond and graphite, have many good engineering properties. But if we go in this case in nano, especially we consider for the graphite, the carbon has the 4 major nanomaterials. These are fluorines, carbon nanotube, called as CNT, graphene, and nanoribbon. So we are totally today concerned in this class about the graphene. So in the all carbon materials, we are going to consider graphene. Then what is graphene? We have to understand. This is our graphite. We have shown in the previous slide. This is shown this kind of structure. And since 1840s, scientists, especially physicists, thinking they are creating ideas, we can separate this layer. But another group of physicists creating big bottleneck, no. Our world is 3-dimensional, so we cannot separate. This is two-dimensional because very, very thin, 1 atom thin. So due to this type of conflict, they are just making some theories and nothing possible. But yes, there was a concept like if we have a book, we can remove a single paper. So here we can also remove, but it is very difficult because the depth between this is 0.34 nanometer. And in this nanometer, the van der Waals force is too much high. You cannot imagine. It's just a saying. If you have a needle and put just a very small amount of graphite, it contains trillion and trillion layers of graphene. So it is beyond the imagination. Scientists are not convinced we can separate this. But it happens in 2004. Professor from the MITs, especially they work also in Cambridge, they get separated these from here. And for this, they got Nobel Prize in 2010. So how it's important, what is the separation is important, just try to understand. Suppose this is our notebook, suppose, and it is tightly bound. We can write. What is the problem? We can write here or here. But now, if we have chance to remove all the pages, what happens? We can write so many things. It is just an example. When we explore these things, we have a huge surface area, huge. And surface area means we can load anything on that surface according to our need. We can manipulate the whole property of the material. We can manipulate the electronic property of material. We can manipulate the electronic properties as well as the mechanical properties of. That was the fantastic discovery. That was the discovery. The discovery is not just separate. They developed a huge theory. What is the impact of this separation from going here to here? That was the Nobel Prize. They not got for the only for the just separation. So this graphene, now we go in this slide just for your recall. This all four material can be obtained from the single graphene. So graphene is called as mother of all graphitic system. How? This. If you have graphene sheet, if you just layer, this becomes graphite. If you just roll it, it becomes carbon nanotube. If you just roll in this way, it's fluorine. It is just not a theory. It can be produced in a chemical lab. If you adopt the different kind of processes, it can produce by graphene this. You can produce this. It's quite difficult, but you can produce. So this means graphene may contain this property of this and this. So all these three properties is one. That is make graphene much exciting than the carbon nanotube, because carbon nanotube discovered previously. So it is created so many hype, so many just application has been developed. But when graphene discovered, all the properties is much better than the carbon nanotube. Reason? Again, we have the role of surface area. Here, if we roll anything, the surface area again going decrease. When we just spread, the surface area go very high. So now Again, one other is it's discovered in 12 and is just 12 or 11. This is another new material, graphene nano ribbon. If we can cut this from here and just try to tilt, then it's showing that it's a totally different property. So this is another new nanomaterial, graphene nano ribbon. So many, it's a deformed, you can say it is a deformed form of graphene, but its properties is giving so many new things. What can be obtained after the deformation of graphene? So now we have 5: fluorine, carbon nanotube, graphite itself, graphene, and graphene nano ribbon. Here, this is the method. They separated. They just taken the stone of the graphite, just rub on the tape, and they applied many things and chemical and like that. For the separation, we will discuss. And they got for the so this simply shows just tape and a piece of graphite, and they got Nobel Prize. But this is not only for the separation. I told in previously, this is due to the separation and for the development of excellent predictions and physics of these nanomaterials. And that is the reason they got Nobel Prize, and they predicted it is correct that the two-dimensional materials can be exist in our three-dimensional world. And it is very interesting, after the two-dimensional materials, so many materials has been discovered, and they are playing a lot of applications. So it's again, you go just in a nano word. It is from my lab. It is just graphite, and it is graphene oxide, and it's graphene. So just it's for your sake of convenience, you cannot convert graphite in the sheet form. And another interesting thing, there is so much flexibility you can see here. But easily in a simple lab, very normal lab, if you produce graphite, graphene oxide or graphene, then you can produce in the form of seed, and the seeds are very flexible, you can see it. So this flexibility is very important for the B composite materials. We will just discuss in the just coming slides. So graphite itself, the same material is not have the much flexibility, but this is have the much flexibility, because here the seeds are spread and we can manipulate the seed according to own desire on the basis of applications. So another important things, nowadays the traditional TV and the we have LED used in the our homes just going to remove within 5 or 6 days. 6 years. Here, if we go in the nano size, suppose you have graphite of the 2 to 10 nanometer, then they are showing amazing different color. The same nanotube, sorry, same graphene. You are getting my point? Suppose if you have a graphene and the size is from 2 to 10 nanometer, then they are showing different color. The same material, it is due to the size. If you have 5 nanometer, it will give emit another light. If you have 10 nanometer, another light. 1 nanometer, another light. But here we cannot obtain any light, and this will be in the coming days. We can produce very excellent TV and LEDs and so many electronic devices using these things. And this is very common. There is no need of very sophisticated lab. You can produce in the normal chemical engineering lab. This is called fluorescent properties of the nanomaterials. So,
what do you mean by size?
Mean size. Suppose we have nanomaterial. Nanomaterials, according to definition, we are 1 nanometer to 10 nano, 1 nanometer to 100 nanometer called nanomaterials. But suppose we have 6 kind of nanomaterial. One have the same graphene. One graphene have the size 2 nanometer. One graphene have the size 6 nanometer. One graphene we have different bottles, and one graphene have the 10 nanometer.
So size is over the area?
Yeah, size of the just seed size of seed, the particle size. Just you can say in engineering the particle size. So if in the not thickness. No, not thickness. It is just always, if we talk about graphene, it's a single atom thing. if we just pronounce graphene, it means it's a single layer, means single carbon layer. So it is the different size of the same graphene. So and it is a general prediction, when you go in the higher size, you get red color. When you the lower size, you just see the blue color. So these are, it's a fantastic, many applications, and now scientists are trying to manipulate these things for the artificial photosynthesis. That is very important for the capture of carbon dioxide. So this is the application. So next, what is how it looks when we just go real world. So for it's very interesting. If you want to work with the ultra nanomaterials, you need a ultra modern facility. This is from our lab. You just please make just a consultation for 2 minutes. Here, this is graphite, expanded graphite. In electron microscope, this is looking like that there is no layer. And in this, maybe trillion and trillion layers. Just we have manipulated some just chemicals. We have just manipulated. You can see the layers. For the good, it's graphene oxide. You can see the layer. Here we have do something other things. Here the layers are get separated, and here you can see this exactly single layer graphene. It's quite transparent. So this is the same material. And even there is no need, this is not a nuclear science. You just go in lab, take a graphite and take a graphene, you can see the amazing work. And that is the reason they have the different applications. Here, if you graphite had just normal conductivity, but this huge conductivity, no any material in this world. But problem is that we cannot control. Till date, we are not able to control the properties of these materials. That is the need of further engineering. So, if you want more information, more exact information, then you have to go for the atomic force microscopy. You can exactly map the thickness of the layer. Here, that it is not from it's the same. It's a China person. They are first time they are reported. By doing this is HR10, that is the crystal lattice we have shown in the previous. So if you go for the more characterization, more instrumentation properties, you can get much good information about the materials. So this is not actually very important. Now, what makes graphene very exciting? So it is only lightest known material in the whole universe. It is lightest known material. Suppose we have the aircraft, how much they are heavy, and that is the reason there is a need of much amount of fuel and this and that. MIT person produce, we just in the coming slide, if we are able to produce the graphene aircraft and graphene based composite, the size and the weight will be 1/4 or less than that, with the more than that efficiency. So we have the thinnest known material, and now there's Indian scientists, some before a few days, they are reported much the other thin material. So another is the graphene, the strongest known material. It's the largest theoretical area. What means theoretical area is a symbol engineering term. If you have 1 gram graphene, you can cover whole your big football. In 1 gram, in a single gram graphene, you can cover totally the football. So another is exceptional conductivity, as I mentioned, and the transmittance, as I am shown in my previous slide, quite transparent. It's just 100% transparent, near about 98 and 96% transmitted. So, but it is also have many problems that need to solve. That is maybe our 10-year work. This is the main problem that we have to engineers, especially we have to solve, the probability of defect. It is when you're going to produce graphene, it needs very pure graphene. Then you get this kind of properties. So there is a chance of always defect. Defect is not due to the just contamination of anything. It's sometimes due to the just wrinkled, just due to age deformation. Many deformation may be. Another thing is you cannot. It is very difficult to produce graphene in the just scale commercial scale in the pure form. That is the another problem. So pure graphene is a big issue. Zero band gap. Here, so MIT person predicted one single layer graphene can bear the load of elephant. So here you can familiar, there is no band gap. That is the big problem with graphene. It's just electron go, come, go, come. There, if there is a band gap, then we can use for the different purposes. So here, the conductivity is much high, we cannot control. So there is a need to increase. The engineers are doing, they are got good success. If we can just push this here, then it becomes amazing material and we can just replace all the silicons using these carbon. So this is the problem. Another problem is now the research as is going on. Previously it is predicted that it's a wonder material and it cannot be, it's a very amazing for the just medical system and like that. But now it has been discovered, it is also showing very, very less compatibility with human body. It means it is somewhat toxic. So there is a need to just finalize these things that they are important, they are intoxic or not, so they are biologically active or not. It's a matter. Another thing is also is there is a need of further create idea how to produce graphene beyond the graphite, because the problem with graphite we have stacked layer. That is the basic problem we are unable to just produce, because the method produced by Andresen, in one day you cannot produce 1 gram. They get Nobel Prize because they are the outstanding just idea. But by the method of the Andresen tape method and mechanical approach, you cannot produce 1 gram maybe in 1 week. So we need to and other substrate from where we can produce graphene. That is the another big task, because the graphite is not mother. We have to, maybe we can design another material and we can convert in the graphene and like material. So many like material have been discovered. So now we are coming to the engineering aspect for the focus point for the composite materials. I think you are all very well aware about the resins, polymers. Okay, so polymers, the laptop, shoes, or cloths, most of the part of polymers. And in engineering, we just easily, in chemical engineering, we told the different kind name of the polymers, but in just other engineering, we just call this nylon resin, PC resin, like that. We can just carbon like that. So what is the problem? Up to 60s, we produce many new kind of polymers. But now producing new polymer seems endless. We cannot produce new polymer. It's beyond the research. Or if we can produce, they are much, much expensive. But it is the industrial world. It is the commercial world. If you are producing anything, it's very costly. No one going to make attention. So now after the 1960, what is the process? If we have 1 polymer and 2 polymer mixed, so we have some new properties, and it gives many good properties. We are using cable and many properties. All these things are mixture polymer. We are only 3 or 4% we are using pure polymers. So this is the concept. When we blend 1 polymer with other, we get some new property. But it also have, every time it has its own drawback. What is the drawback? Maybe they have the very less compatibility, then phase separation, then mechanical property get decreased. Okay. So what is for this? Scientists design, they added some compatibilizer. Suppose some just make mixable much. So for this, after the 90s, they started working something called compatibilizer, some filler. So these fillers also created a lot of attention of the industry, and we can produce. Here, there are so many gaps. Here, the gap between the resin and the filler is very less. So properties is very good here. But again, when we now in 2010 and onward, the researchers are trying to remove these things by the nanomaterials. And in all nanomaterials, carbon nanotubes, graphene got a very much attention and real-time application. So many so many composite materials are available in market, and for the just very high stage just composite, for the advanced composite are available for the advanced applications, especially for the elevated temperature using the nanotubes. So they are very, very stable at the high temperature and pressure. So how it can work? Here, as we know, we engineer, I think you are much aware, we are using 50 to 60% in the aircraft, and they are use the carbon and many carbon and other conventional fillers. So now the scientists are trying to replace these, the composite using the graphene, using carbon nanotube, using graphene nanoribbons, or using some inorganic nanomaterials. So that is the prime aim, because they can give high flexibility, improve thermomechanical properties, create resistance, and easy processing. Then, how it can be? Just a very common example. We are all familiar with polycarbonate. Polycarbonate is everywhere in our homes and everywhere. So this is the different application of the polycarbonate. But what is the problem with polycarbonate? Because we can, if we have iron and we have just coated with the good materials, we can use up to 10 year or 20 year or more. But the polycarbonate, what is the main problem? After 5 year or 6 year, these are the problem. These are the reported problems: swelling, fracture, and cracking. So scientists are get 100% recovery if we can use by these nanomaterials, because if we can use the single layer graphene, it will be transparent. So transparency of the just polycarbonate will be maintained. It may be sometime, now it is maybe high, in coming days it will be, if the research is going and going, it will be very cheaper. So, and crack, it will can be we can recover. Cracking we can cover using these nanomaterials. So it would be our aim that we can reform or we can reconstruct these reused material are cycled. It's a huge amount of polycarbonate produced every day, every year. So we can recycle these materials by using different kind of nanomaterials. And these polycarbonates is very, very significant for the engineering application. So this one be a very good things that we can produce this kind of polycarbonate and other transparent material we can do with these nanomaterials. Now we come to another example how it make very mechanically strong when we use the carbon nanomaterial. Especially now we're talking about the carbon nanotube. Here the carbon nanotube is just like powder. If you purchase in a bottle, it's just powder, nothing. You go in the electron microscope, it's looking like that. Its structure is this. When anyhow, so this is, suppose this is matrix, this is our fiber. If we, without, it is not here, then they are just separated alone. When we mix CNT, the property of CNT, they get entangled. Here you can see. So when the layers are tightly entangled, what happens? Thermal properties, mechanical properties get increased hugely. This is MIT report. This is I have given the references in the last. And this is they propose the mechanical properties, how the matrix and the filler have the interaction between these things. So these kind of this tube-like nature. Obviously there is a need to many processing. You cannot use just mix in the carbon nanotube and you get this property. No, there is a need of some processing like consolidation and like that. We will discuss. So this is the properties in the real time we can obtain for the polymers, neat polymers. So we can stop producing new polymer or need a very advanced stage polymer. We can manipulate the existing polymer for the elevated application, for the advanced application using these nanomaterials. Because these materials are just advanced. If you must keep in mind, in engineering and science, 10 years is nothing. You have to invest much time. In 50 years, it's taken as new invention. So this is just a 10 year or 20 year. Our coming days, we are very hopeful that we can produce all our recyclable material for that industrial applicable form. Now, why it is? It's an amazing presentation. They give you a simulation using this is also MIT work. They produce why this can be is very giving the excellent property. So you can different type of we test the mechanical strength, tensile, compression, and can be a huge load, and it is estimated it's more than 20 times much stronger than steel. And if you talk about the graphene, it is 200 times more, more stronger than steel. So we can use these materials for the real-time application. Yes, obviously there is so many challenges, but there is a just for the mind awakening things that we new mind, we new young people, we have to consider what we can do with these materials, because it is open to all. Before, just you going before 50 years, the science are limited for the few peoples. Now we can think, we young people can think and can resolve many problems, our civilizations. Next, it's from my research, it's a published work. If you have the polycarbonate, if you have polymethyl methacrate, PC and PMMA, this has own properties, own good properties, it has own good properties. They all have the drawbacks. PC have some drawback and PMA have drawback. So we have tested, first time we have tested, it's a very engineering method, we have mixed in the using just graphene, graphene oxide. This is not, it's a result we are just talking about for your introduction purpose. Here, this is neat one. We have mixed just both polymers. So you can see easily there is a lot of cracking and very big shapes and wires. And in engineering, you know, if there is a no homogeneous distribution of the system, you cannot get the desired properties. So here, there is so many cracking. This other work is not shown here. We have tested 6 or 7 samples. But here, when we mix with graphene oxide, due to the functional groups, you can see there is no such kind of cracking. So we can resolve. It is just a prediction. It is just for the reality. It's just for the prototype application. But yes, we can produce. But what is, you may ask why we mixes? What is the need of mixing? It is very costly. PC is very costly. First thing, it is little bit costly. So another thing, if we have to produce just 10 kg, the 10 kg price of it will be very high. If we mix, first is our price. Second thing, the PC is very much sometimes excessive toward the humidity, but this is not. So if we mix in the proper ratio using these things, we can control, we can manipulate in the simple things, we can manipulate the properties of these materials. So this is the result. It's just for your introduction that how graphene work, how the fill the gap, how it is work. You can also find this of my paper on internet. It's a very easily, everything is when how the cracking has been removed due to the introduction of these materials. Now it's just for here we have the neat PC and PP. We have mixed the other samples also in the different mixing sequence, but in the good sense we are getting this kind of tensile strength. So we can control. Yes, obviously there is a need of a lot of work. We can work with a lot of system, lot of polymers. For these things, we can produce some advanced composite in our lab. Maybe at present they may be a prototype application, but in coming days they will be very, very important for the advanced engineering, because the engineering is everything, science is everything changes. So we cannot just wait about these only conventional polymer. We have to do something. Thank you very much to all of you. I am very grateful to Professor Ha for providing me this opportunity. Thank you very much.
Well, any questions?
Yeah, I'm very happy if you have any question. Any question, if you can ask, you maybe beyond the slide, you can ask. And if you want anything repetition, I can repeat. If you have any problem from initial to here, you can ask. I will be very happy if you ask.
Wonder any real applications using graphene?
Yeah, that's I am in this slide is.
Yeah, what I mean by application is not just material aspect, but yeah, this kind of a real application is a product.
Yes, I'm showing product, and this product is in the market.
Right.
these products are in the market. This,
Okay.
but the cost is very high.
Yes. At this point, they are on the development stages.
Yeah.
Right. And what are the barriers for real productions? And you mentioned several points.
Yes.
But in your opinion, what are the real barriers?
Real barrier is the obviously production, bulk amount of production in pure
Production
form.
process.
Bulk amount of production in pure form.
Pure form, without any defect.
Yeah.
It has a very consistent geometry.
Yes.
Do you think it's possible?
Yeah, it's easily possible. It is possible.
What do you suggest to mechanical engineers?
Actually,
in terms of design of certain structures or certain materials?
First I want to suggest, it is very interesting if you just Google on these materials. They are mostly, the work is performed by the mechanical engineer. The interesting thing is that most of the calculations performed by the mechanical engineers. So this is the new word for the mechanical engineer. We can work together to fabricate the material, not about the graphene. How can we produce a new material using graphene? For example, we have taken an example of the polycarbonate. How we can work to produce, we can try to recycle all the polycarbonate using these materials. This only a good chance for the industrial application.
Okay, so let's go, one by one. Say supercapacitors. We do know that supercapacitor can be used as a battery, right? Can you say a little bit more about this?
Yeah.
Supercapacitors.
Exactly. When you need very high amount of energy at once, battery is giving energy just slowly by need, for example.
Power is very low.
Yeah. Well, it's a very tremendous energy for the 1 second. Then you need supercapacitor.
Using a layer of the graphene.
Layer of graphene, because graphene is very conductive, so we can manipulate and just we can just insert the electrolyte between the layers, right. So they can easily transfer the electron. So we can produce these kind of hybrid. They call hybrid supercapacitor.
So we can store as much as energy as in the lithium battery, but the great advantage with this supercapacitor is how fast you can discharge the energy. That gives us a power. In a lithium battery, the energy content will be the same, but we cannot take it out very fast. So the power is relatively low.
And also very important in supercapacitor when you're talking about graphene, the lithium is very limited. Lithium, lithium material. Our whole world depends on China. So we need our material.
Now we have a North Korea. North Korea has a lot of lithium.
No, they're rich, but they're processing. They are presently, what I know, maybe my knowledge is limited. Presently, Korea is not providing lithium to others. So we need our material. So graphene is graphite is available everywhere. You can purchase 1 kilo, 2 kilo, or many.
Okay, how about the what is that?
Environmental protection. Yeah, that is concerned with the carbon capture. Yes, that is suppose there is so many carbon dioxide just produced in our atmosphere, but we at the present we don't have any system at a good container that capture all the carbon dioxides. How that is? So if we have the functionalized graphene, the special kind of functionalized graphene have very sensitive. That's a sensing property. That's an intelligent material called. They have sensing. They can capture all the carbon dioxide. If suppose we can produce just set a plate for the just solar cell. We are using a different kind of solar cell. So we are getting the solar energy. Suppose we are developing such kind of material and produce just plate every in whole city. So they are able to capture all the carbon dioxide. If they capture, there is a need of engineering. We can store that kind of carbon dioxide. And if we can produce that kind of carbon dioxide, then we can easily manipulate. At the present, the problem is we are unable to just absorb all the carbon dioxide from the system. So these materials may be very, very, very useful. If we can absorb these materials.
How? Why?
That is the graphene and functionalized graphene have a the functionalized graphene especially have the very strong affinity to the carbon dioxide, so they can capture. They have very strong affinity, so they can capture. And if as soon as they capture, there is a need of engineering these two.
Okay. So there are such a application.
Such a application that's we can
have.
Yeah.
Okay. How about that's
the next. The molecular structure, new molecular structure we can design. For example, for water purification, we can when we are using the molecular sieves and many things for the water purification, what happens? So most of they are inorganic things, means like nanoclay, and these are presently so many resins are used. But when we are going to carbon materials, the surface area is very, very high. And if we can design the molecular sieves using the graphene or the carbon nanotube, they may be very, very cheap and very, very efficient. So molecular structure also very important, maybe the coming aspects. Just polymer blend we have discussed. The smart and intelligent material. That is another material. The part of nanomaterials, they have the certain kind of just intelligence, you can say. If you manipulate such kind of, suppose if you just put graphene here in layer wise, then the probability of passing electron from here only, there is no effect here and here. So this kind of circuit we can develop, because most of what is the problem of the speed of supercapacitor? We engineer know most of the energy be dissipated, just dispersed in the other forms. So there is a need of just point to point dispersion of energy, point to point hopping of electron. So we can the smart and intelligence material we can use. The 3D printing.
And also something like the sensors,
right?
Made of the graphene and
CNTS, that is reported.
Implement into structures.
Yeah.
So we can detect some damages and some called health monitoring of these structures.
Yeah.
So whatever happens in the structures, these materials can detect and send us a signal, so we can do something before anything happens. And the 3D printing.
3D print. 3D for the 3D paintings also 3D paintings in this aspect I am talking about how graphene can be used. It's not about the engineering of I'm not much aware about what is the engineering of 3D printing. Suppose actually if we have if we have instrument and if give the graphene coated graphene material coated with something just initial information from the instrument, so we can print using the graphene. Such kind of thing is related to that.
So enhance
mechanical properties.
Yes. Well, 3D printing, as you know, FDM use polymers, but we like to enhance the material property, but it's very difficult because we have a very small nozzles and we have to make structures. And so we are adding CNT and graphene in the polymers, and so 3D printing
nano and hybrid nanostructures. That's other material we can be inspired. There are so many materials can be maybe discovered in future, inspired with these materials, because the engineering is always just ahead. We think ahead. So maybe graphene, if we think about graphene more and more, we can get a new material, because some Indian scientists before a few days, they reported even thinner material than the graphene. They are reported in I think in Science. So maybe if we work these material, we maybe explore new nanostructural one.
Okay. And again, nanosensors for bio applications and drug delivery is very important. Transparent.
For us, for mechanical engineers, very important this one and this one. How can we produce flexible materials? How can we actually process this material to in the complete flexible material? That is the big issue. This is even in market, but it is very costly. The Samsung is just stopped production. It is in market. There is just a very efficient one. This is also. But actually, it's a very due to technical problem. So we can think, leaving all these things, we can consider the polymer composites, nanocomposites, this and this. We can consider this.
Yeah. Speaking of flexible materials, there will be a big application such as the wearable device as a sensors, and that we need many different types of electrical properties. At the same time, we like to have a mechanical strength as well. Also very flexible. That is the material being developed a lot. We had a Professor Bao in Stanford. We hope to show that very advanced applications and research, mainly in chemical engineering. But now there is no barrier between department, mechanical, chemical, or whatever. That's all the story. Nowadays, we engineers, we need to have first of all knowledge and imagination, and we can create our own application and materials. So we again need to extend our concept. And okay, I hope that we have another chance.
Yeah, sure.
And more deeply, deep application-wise, and you can pick some interesting applications, so flexible mobile applications or wearable device. Anything will be okay. We hope to have another speech.
And also, actually, if you have any suggestion, then I can modulate myself, because if I'm giving 1 hour, it would be my potential that I can excel something. So if you can give me your maybe some speaking style, maybe presentation style, maybe so many things, bad things. So if you give me your feedback, if we have to continue this class, we can improve more and more. We can use chalk and the blackboard and also these things. But it depends on you. If you are interested and if you give that little feedback, then I will try my best to, because I also want to actually just learn with you. It's not nothing. I'm
Sure,
nothing.
yes.
We have to learn. Maybe you have a very new idea that we can work in the coming future.
So I hope.
Yeah.
Okay, sorry. I hope to have next time 3 hours lectures, and again, thank you so much. And Santos just joined our lab to continue to work with the carbon. We mainly on the composite. Carbon fiber reinforced, glass fiber reinforced, but I like to learn from him, and then he will stay in our lab to create new applications. Well, what kind of application? We don't know yet. We like to exchange information, and we create new applications. That's what the research is. Okay, thank you so much.
Thank you, sir.
Okay, thank you.
Thank you.
Okay, let's have a 10 minutes break. Okay. Yeah, now you can pick one specific applications. Specific applications and can discuss. You like some?
No,
You want some drink?
no, it's water.
Yeah, let's have some water. Oh, thank you, thank you.
So I'm going to room.
Okay, okay. So I will catch you. Thank you so much.
Thank you, sir.
Yeah.
Thank you.
양쪽에 물질 양쪽에 물질
셋업 좀 해줄래? 엑셀도 좀 열어줘. 그래프는 없나? 그래프가 중요한데. 왜 그래프를 안 했어? 그럼 결과를 어떻게 내? 여기 그래프 있네? Okay. Last week we programmed failure index based on the SIU failure index, failure criterion. Okay. Let's see. Okay, I like to add plotting graph, failure index. Say this one. I like to. This is the failure index K. I hope you can see. Failure index K, failure index K1 mean that each ply you have a bottom and top sub positions. So we do have a name, and then let's say this one. The name was what? F-I-K. So F-I, K-ply, and F-I-K. Why not? Oh. 이 이름이 L이라고 한 거야, 이거 한 거야? So, okay, as you can see, we have a ply. Each ply we have, starting from the bottom, first ply, but again, we have a top and bottom of each ply. And second ply, we have a top and bottom and up to 10 plies. We have up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plies. So we got failure index using strengths. Okay, this strengths has to be called from here. We do not have a, we need to define the material strengths here, each material. So you can define the X and X prime and so on. And then material property need to be called here, but we just enter the values. For now is okay, but it needs to be called according to material property we specify. This is the material number 4, and all the material property has been called, right? Okay, so we have a failure index, and we can plot the Z coordinate failure index. Okay, here is the failure index. The horizontal axis is along Z direction. Okay, this is a thickness, and this is a failure index. Okay, let's double check whether this graph makes sense or not. Well, thickness is chosen as 1 for each ply, 1 millimeters. And the angle, cosine isotropy, 0 + 4590 and symmetric. And now we have a moment 1 and moment 2. Let's start with a simpler load. And N1, and as you can see that, well, this is nothing. This one is a top and bottom is a symmetric. This is the bottom, and this is a top, and this is the all symmetric with respect to a neutral axis. Why this one is the higher? Because of this 290 degree. 290 degree. This is the subject to a N1, one directional load, 0 directional load. So this 90 will have a weaker strength. That's why we have a weak, higher failure strength. Higher failure strength means higher stress. So if we pull in every one and 1, 2 directions, and you can see that not so clear. Failure index is a uniform, not 100% sure. Just 1 second. On axis stress. Yes, yeah, it's not that straightforward, but it makes sense. So cosine isotropy, we applied N1 and N2 is all the same, and every ply will have show the same failure index. And now you can see that this is very important procedures. Look at the value, okay? Look at the failure index. Failure index is up to about 5, 10 to the minus 10, okay? Which means that if we increase this much, increase inverse of this, say we increase approximately, okay, 5 minus 10. Let's see what happens. Now you can see that all the failure index goes to very close to it's not quite correct. Why going top and bottom is different? Well, this is the Okay, let's change it to all zero. Well, as I emphasized before, we are all often facing some bug, and I'd like to share with you how to fix the bug together. Say we program and N1 and N2 we apply, and all the 0 degree. When you have some bug and error, how do you know this is bug and errors? Well, first you need to have a rationale. How come it's up and down, they are different. This is certainly is not right. So to find what caused the errors, we always need to simplify the problems. Simplify means, let's say we make all the 0 like that, and we say even simple goes like that. This is okay, and now, oops. 왜 값이 이렇게 So strange. If we change 100, the value will be uniform. But how come the value is not uniform? Anyhow, let's find out what caused the problem. As you can see, top and bottom for each ply have to have the same value. So let's see. K ply. Here, this guy and that guy, they are all same. Oh, I'm sorry, I didn't pay my. Oh. $5.4, 5.8. Okay, let's go, and then okay. So this is the point. Here, failure index. The bottom one is a 5.8. Top is a 5.48, and second top and so this one is not continuous. That is not right. So let's find out. Here, this guy is the AB, and these A and B, in the theory, we have a A and B to calculate R, right? And this A and B and this A and B, they are different. So I think this one refer to this, and this B refer to, okay. Now this one, how about the stresses? Well, as you can see that this stress and that stress-wise, okay. The top and bottom surface of each ply, they have the same stresses, but why this one is different? Can you see that this one and that? You can see that this and 2, there is a 2, okay. See, there is a twice of 2, right? So that is not right. So now you can see that they are same value, and let's copy and paste. Okay, so now we are all the same uniform value for, as you can see, all 0 degree, and we are applying N1 and N2 same magnitude, and we have a failure index uniform. I mean, they have to be uniform. Now, what I like to emphasize is the failure index of 6. 6 means 6 times higher than strength. So then how much load this plate, I mean the laminate, can support? Can you easily calculate? Yes, we can. This is a 6. What we need to do is just divide by 6. Divide by 6. It's not a complicated procedures. I like to give an engineering sense that, you know, all the failure index, we have to design so that failure index of all ply have to be 1. Then for that purpose, we just decrease all the load level proportionally. This is the important point. Proportionally, we have to divide all the same amount. Then this will just, you know, go up and down. This is an important procedures. Now, this N1 and N2 is a in-plane load. What is the in-plane load? N1 in-plane load is the stress times thickness, right? In-plane load is the stress times thickness. So let's think about this one. Only N1 direction, we apply this and all 0 degree. And what is the thickness? Well, thickness now 8 has no unit here. Okay, the unit, we need to be very careful, obviously, in every tools and CA tools and even CAD program, especially in CA tools. They don't have any unit system. We designer have to choose unit. Unit have to be very consistent. If we choose this one, for example, EX, EY, and all the material property is the Pascal, right? So Pascal is the unit we chose, and then all the dimensions better to be meters, right? Meters, and load has to be Newton. So if we say 1, meaning that this is the 1 meters. So this one, okay, let's choose thickness. Well, this one, I'm sure we didn't pay attention to a real unit, but let's make it to a real unit. Say to make say 0.125 millimeter is the conventional ply thickness. So 0.125. This is the meter. So as you can see, that total thickness is the 0.00 meter. So this will be 1 millimeters. Now we applied the N1. Then in terms of stress, how much stress we are applying? In terms of stress, I will enter here is a stress. Stress has to be N1 divided by this total thickness. That is the stress we are applying. Okay, that is the stress we are applying, considering thickness. So this is the 333 gigapascal, right? Gigapascal we are applying. As you can see, the failure index is the 200. So what's the value? 0.222 point. Okay, so let's divide then as you can see, failure index will be precisely 1. Then as you can see, this is the stress we are applying. What does this value, what is this value related? Okay, this is the 1.5 gigapascal we are applying. What is a 1.5 gigapascal? Well, that is the strength he chose, 1.5 gigapascal, because this is X directional strength, and we stack as many as we like, and we applied N1, but strength-wise, this is the 1.5 gigapascal. So this, as you can see here, it reaches the 1. Okay, I'm trying to explain what the failure index means in a simple way. Now you can, similarly, you can apply to just one y direction, okay, y direction. We don't know how much N1 we need to apply in plane load. For that purpose, again, we just apply unit load in 2 directions. And as you can see, that failure index is 0.000025, very low, which means that we can increase the load, right? We can increase the load by how much? As much as failure index. Then you can increase 1. And this is the amount in plane load you can apply. And stress-wise is the 40 megapascal in N2 direction, which means that what? This is a 0 degree, and N2 direction, meaning that 90 degree transverse tensile strength, right? Transverse tensile strength, which is the, I'm sure this is the, and y directional tensile strength. That's the amount you can apply, and material will fail at that point. Okay, so now you can say, you know, any load you can apply, any load, and how much failure index we have. Well, only one directional load is easy, but multi or biaxial load, such as this way, is not easy to predict. So as a designer, how much we have to we need to apply by just looking at this one. There's a 1.158, and then you can divide 1.158 and as you can see that now failure index reaches the 1. So this way you can find the strength of a laminate. In other words, let's say you have many different angles, 45 minus 45, and typical one is the this kind of a quasi-isotropic. And you have a 0 plus minus 45 symmetric, and now you need to apply this much load. And as you can see, failure index reaches 4. So you have a two choice to reduce this one. You can see that you can reduce by factor of 4. Then, oops, probably a little. not the 4.01. 4.01. And same ratio, something is not right. Something is not right. The maximum value is precisely 4.014. And how come we like to multiply this variable. And then we divide by 4.01. And how come its value is a little smaller? This is not right. Okay. Let's define the maximum of this failure index. So this is the maximum of a failure index, LK. And this one also maximum of this one. Okay. So let's say input, and this is the maximum failure index. Maximum of failure K, K1. Okay, what I'm trying to do is that change this input and see how this failure index varies. It's certainly proportional to this load. Yeah, do you see what I'm trying to see? And as you can see, this input value goes to here, proportionally increase the load, and all the way you go, and then come back to this failure index. So whatever we change, this as you can see, that failure index is the increasing. So let's try to start from the point 1 to a point, how much? Okay, we can go 1 and 0.01. Yes, it's pretty much linear. Not quite linear, huh? But something is wrong. Yes, something is wrong. Very difficult to find because if value is very large, then easy to find. But this one value is very small. Anything less. Huh. Okay, well, it is certainly has some bug, very small bug. Smaller bug is more difficult to find. But let's move to a next one, and then I will get back this one. Today, what I like to do is but you can see the idea. What is the meaning of the failure index? What are the load you apply? Okay, it's not much magic things. It's just a failure index is represent stress level. Okay, if we increase the load, the failure index will certainly increase. But there are so many different stresses, sigma x, sigma y, and so on. But failure index only one value which you represent the strength level. It's very easy to help us design structures. So now I'd like to add a temperature effect. Temperature effect is as important as the mechanical load. So let's get back to, it's called thermal stresses. Okay, thermal stresses. What is the thermal stress? Well, these thermal stresses or thermal expansion mismatching could happen to any structures, any products, any materials. Not just for the composite material, even for the metals, especially say two different materials bonded together and subject to a same temperature, then it will unexpectedly deform. Mainly why? Well, there are two different issues. One is the two different stiffness, two different coefficient of thermal expansion, we call CTE. So two-way, two is the two material properties are causing these thermal stresses inside. One is the stiffness, the other one is the CTE. Okay, I'd like to review about the CTE and a very simple concept of the temperature effects. Say we have a certain material, okay? Certain material, well, say this is the steel or aluminum. And we increase the delta T from references. We always like to observe the stress or strain. Where stress, we have a three-direction strain or three-component, etc. But forget complicate one. We always like to pay attention to a one-dimensional case. Sigma, is it this direction is changing, and strain, is it this direction is changing? Well, we can say here, right? Sigma or strain. So when we have a temperature increasing, the point is that this is a free boundary condition. Free boundary condition means it freely expands. freely expand. So we can see that there will be no stress. Why? It's a freely expand, but strain is certainly not. There are certain amount of expansion. That is a starting point. Now let's recall a stress, strain, temperature relations. Usually sigma epsilon, that is the material property, stiffness relating stress and strain. But if we have a non-zero temperature, there is the temperature dependent terms, and strain is the proportional to a temperature increment. That coefficient is called CTE alpha. Alpha is the coefficient of thermal expansions, called CTE unit. Since this is the C or F, alpha is the simply 1 over a C. Okay, so this alpha is very much material property. Okay, material property. Say steel, you have a alpha. Aluminum, you have a alpha. Alpha is about range 10 to the minus 6. Multiply 10 or 20 or 60 or whatever value. So say you want to have a 1% strain, you can see that how much temperature you need to increase. And as you can see that if the temperature decrease, the material like to shrink. And temperature increase is increase. Okay, this is a very simple, this is called a constitutive equations. And we used to have a strain and stress, but we do have a temperature term. So stress, strain, and temperature relation. This is the a basic mechanics of materials. Now, we like to constraint and both way, and then increase the temperatures. What will happen? Okay, sorry. We have another, the same one, same materials, but we do have a different boundary condition. And this boundary condition will constrain these structures from expansion. So in this case, again, delta T increase, the sigma or epsilon now has a 0. Why? There is no free expansion, the 0 strain. So to meet this zero strain, this stress has to be non-zero. There's a certain amount. Actually, it is a compression and negative. So if we look at this stress strain temperature relations, this is a free, sigma equals 0. So strain, stress is equal to 0, and alpha delta T. As you can see immediately how much we have expansions. Okay, depending on how much temperature we increase. Now, same equation applied to this second case. Now, strain is 0, and stress E plus alpha delta T. So, sigma, you can see that minus E alpha delta T. This is the compressive stress has to be developed inside the material to meet 0 strain. Okay, this is very important concept. So as you can see, the stresses inside will depends on the material stiffness and the temperature and CTE. So this is the stresses. Now we like to have two materials attached. Okay, two different materials attached. So this one, okay, this one, say very soft plastic. And this one, say very stiff steel. And then we increase the delta T. Then plastic, imagine what will happen. This one still like to expand, and plastic like to expand. Let's not consider bending, okay? Just a free expansion in axial directions. So the bottom line is that they have to expand together. Why? Well, they simply bonded together. So they have to expand it together. So steel and plastic, how much is stress and how much is stress for each ply, each layer? We don't know. Now, we like to calculate. So to get the idea, let's pretend that these two plies are not bonded. Not bonded means that, okay, plastic like to expand this much and steel like to expand a little bit less. So this one was the original length. This one was the original length, and delta T would give us this much free extension and this much free expansions. But the reality, they have to deform together, so deformation will be over here, which means that this steel need to expand, subject to a tension, and this a plastic subject to a compressions. So this force and that force, they have to be same. Why? Because externally, no F. We don't apply any external load. So this is the sigma to a plastic, sigma to steel. That is the compressive stresses needs to be developed in plastic, and tensile stresses needs to be developed in steel. Okay, it's called compatibility conditions. Now, when we calculate this sigma, we have to meet strain sigma, Young's modulus and alpha delta T. This is all steel, plastic, and steel. You have a same equations, but this one is the plastic. This is steel, and this is the plastic. So total force, equilibrium-wise, a force have to be same, and strain have to be same because they deform together. And from these two conditions, we can calculate. So how many equations? Let's count. Total force have to be same. So F, I can say thickness plastic times a plastic stress plus the thickness of a steel and stress, right? So these have to be 0. There's no external force. So this is the one equation. And another equation is this is a plastic, this is the steel. These two, plastic strain and steel strain, they have to deform together. Why? Again, they are attached together. So this is a geometric compatibility, and each one has the constitution 1 and second. So how many equations do we have? It's very important to understand. Material properties 1, 2, and geometric compatibility 3, and force equilibrium 4. So we have 4 equations. How many unknown do we have? Well, we have a strain, stress, strain, and stress. So we have 4 unknown, and can be calculated from these four conditions. Okay, so this is the very important concept. And of course, in real world, if we have only to apply this geometry, wise, this will bend like a bimetal. In that case, we just modify this one. We will have a curvature, but conceptually similar to this. Now we like to use this concept, extended concept, apply to a composite. Apply. Now this each ply would have a, this one is not just a 1D. We have this stiffness and transverse stiffness and shear stiffness and CTE, this alpha, it has a, this is alpha X and alpha Y, and all different material property. And this one also all different material property. Why? Because each ply would have a different angle. Now different angle, meaning that this way, even though these are same carbon fiber, now we have a different angle. So this expansion and that angle ply, this expansion, they are all different. So different CTE, different stiffness will cause a will meet the deformation conditions and equilibrium, and we would have a very significant stresses. And this one is particularly important in composite materials because the composite, we have a curing process. Curing process during the manufacturing process. Let's say this is all the plastic, carbon fiber in there, and then we heat it up. We need to heat up like 100 Celsius. All material is, the viscosity is very low and free stress, and then cool down, and all stiffness will increase, get hard, and we have expansion. Like now delta T, in that case, delta T will be negative, shrink down, because stress-free at the high temperatures, curing temperature, no stress, nothing, stress-free, and then cool down to a room temperature, there will be inherent thermal stresses that would cause the residual deformation. That's why in composite material, whenever we would like to make manufactures, we did mold, we lay up and cool down, always there's a distortions, big problem. And as you can see that using our theory, which we're gonna study right now, can be used to roughly estimate how much deformation we can have in the composite materials. Simply the way is that starting from the high temperature, curing temperature, say 100 to 25, so minus 75 will cause this structure will deform, how much it gives us a deformation. That's the simple procedure you can use for complicated structure using CA tool. Sometimes they are using very sophisticated curing process and sophisticated resin flow analysis, but sometimes too complicated. But as I mentioned, simpler way is just consider high temperature, cure temperature and room temperatures. That's the easy way you can do. So anyhow, that is the one simple example of this temperature. Now, concept is exactly the same as in the isotropy material. Now, we have a on-axis and off-axis because, again, even though this is the same ply, but if we change the rotation,
the material property in this direction is always changing, right? It becomes changing, the material property are changing. So this is the own axis. Own axis, material stiffness, sigma, q, epsilon. Now we have a alpha delta T, same as in the isotropic material. And alpha is not just a one value. We have a alpha and shear alpha. Well, there's no shear alpha, but three terms, but this is the alpha x, alpha y, and then no shear. But anyhow, this is three terms and delta T. So this is the own axis. We like to see what is the alpha. And then with respect to reference directions, we need to rotate over axis. So stiffness are different and CTE are different. And then this guy, we need to stack them. So behavior like we have all different materials stacked. Okay, different material. Because in reference direction, they have all different stiffness and CTE. And so we stress temperature relations. This is the thermal strain terms. And if we this term goes left, then epsilon minus alpha delta T times Q. Q is the S inverse and sigma. And now this term, what is these terms? And this conceptually very important to remember. This is the what? Total strain. Total strain is the what we observe. What we observe. The total strain can be caused by mechanical stress and thermal strain. So from these equations, this is a total strain minus thermal. What does it mean? This is a mechanical strain. So mechanical strain times stiffness will be a stress, right? So not only by equation, we need to understand physically. This total strain is what we observed, and this is the thermal strain minus this left term will be a mechanical strain and multiply Q. Okay, so the new term here is the alpha x and alpha y and alpha s. Alpha x is the term when we increase the delta T is a expansion or decrease. Well, the CTE usually positive, but doesn't have to be positive. Carbon fiber, especially itself, is a slightly negative. Slightly negative. So it's a carbon fiber. If we increase the temperature, and carbon fiber shrink very much small. But stiffness is very high, so the effect can be sometimes very high. And y directional stiffness is the positive and negative is expansion and contraction. And shear term, shear temperature is a increase, we will have a shear or not. But by symmetry, this has to be 0. Okay, by symmetry, we cannot have this terms, so this one is usually 0. Okay, so this is the material property, stress, strain, temperature for each ply, and now we like to stack them with the different axes, as I mentioned. So this is the equations, and we do know how to change Q from Q to Q bar, and we need to know how to change, rotate alpha to alpha bar. How to do that? Well, alpha delta T is nothing but strain. This is a strain. So alpha transformation is the same as the
strain transformation. So this alpha 1 bar is alpha x, alpha y, alpha s. We need to apply. M is the what? Cosine theta. Okay, this is the theta, cosine theta, n is a sine theta, and we using this multiplication and to get this one. This one is from a strain transformations. But again, as I mentioned, this term usually 0. So we don't have to consider these terms. But as you can see that alpha 6, what is alpha 6? Alpha 6 is like this. And then temperature increase, this will have certain deformation like that. Shear strain will develop. Shear strain. That is the alpha 6. Alpha 6 is a non-zero because of this alpha x and alpha y, we have a certain angle. Okay. So now we are ready to go. We have a constitutions, and then we go through the way we have done in defining the load, in-plane load and bending load. Only difference is that we use the this stiffness equation, and this is the, as I mentioned, is a total strain. Total strain has the in-plane and curvature, and put into here. That is the off-axis strain, because this one all plies are glued. That's why they have to have an in-plane strain and curvatures. And now this is the stresses by definitions. All stresses summations will be an in-plane load, and all the in-plane stresses multiply z, okay, multiply z will give us the moment. Okay, so this is the one, this, and that, and that. And these are all equations we need to have. Okay, this is the deformation compatibility. Each ply have to deform either straight, expansion or bend. And this is the constitution for each ply. Again, this Q bar and alpha bar have to be transformed from on axis. And this is the external load as we did the in-plane and bending moment. Now, all you need to do is just put it here. Okay, sigma bar is put this one into here, and this epsilon bar put these things. So this one and that. This is exactly the same procedure we did to drive A, B, D matrix. Only terms we are adding is the new term, this guy, and see how it goes. So integration, okay, integrate over the thickness, integration. What is the epsilon 0? Epsilon, this is the in-plane strain. This is a constant over the z, right? Constant. Only z dependency is this z there. So this is a constant, and epsilon 0 is out of integrations. Now second term, q bar and z and dz. Q bar, by the way, as we all know, this is a function of z, right? Function of z, because all the rotation, that term cannot be out of integration. But epsilon z and curvature is the constant out of integration. Now this is a new term. And Q bar, alpha bar, and delta t. This is the new terms, and this is the term we have to calculate. So if we put these terms on the left-hand side, and we will get these terms, N plus NT. This NT is not the external load. As you can see, it's only due to temperature and material properties. Now, similarly, we let's go through a moment, sigma z, and exactly same, there's a z there, and integrations, and q, and epsilon 0, and curvature is constant, and this is the, as before, B matrix and D matrix. The dimension is as you can see, this is a 3x3 matrix, right? 3x3, all 3x3. And now we have a new terms, Q bar, alpha bar, and delta T, and Z. Again, this is not the external load caused by the delta T, and this term is minus. Let's put on the left-hand side, we have these terms. So this is a BD, so BD, AB, so AB, BD, epsilon 0, and K, and now these terms, new terms. So these new terms are added. So these are external load we are applying. So we have lots of layers, and we have a N1 and moment. Now we apply delta T. This guy would cause this much, these terms. Where are they located? It looks like same as the external load. So imagine even though we don't apply any load, the delta T will act as the external load, which would cause the epsilon 0 and curvature. So let's say we have a plate and a layup sequence, increase temperature, it will extend it and bend it. And conceptually, as you can see here, Q alpha delta T. Q is what? Stiffness, alpha CTE delta T. That's exactly the same as what we observed here. Q alpha delta T. That's the amount of stresses, external load caused by delta T. Okay, when we have a constraint, so when we have a stack them, a constraint by other ply, it cannot freely expand. Constraint by the other ply, so that much stresses will develop E alpha delta T. So stiffness, CTE, and delta T, that is the act as the mechanical load, thermal load. And here we have a Z terms. Okay, so to consider temperature effect, what we need to do? We need to do program NT and MT, which is this guy, this one. Okay, that's the one we like to cover today. And imagine that Q is the dimension is what? 3x3 matrix. And alpha is what? 3x1 matrix. So Q is like this, Q11 and Q12, and alpha is alpha 1, alpha 2, and alpha 3. And then you can see that this is the A vector. And vector, and as you can see here, N is also a vector, 3 terms. Okay? Okay, so so obviously this week, the homework will be to calculate all the thermal stresses, how much stresses will be developed
depending on the layout sequence and temperatures. And as you can see, we have all the failure index. This distribution is also caused by delta T, just the temperature. We have all the distributions, and the highest will subject to a failure, material failure. As you know, the composite can easily fail just with the temperature. Using these tools, as you can see that you can predict bimetal, means aluminum and steel. You can, all you need to do is just changing the material properties and then temperature, and you can see how much it deform like that and deform like that, and then how much stress will be caused in each layer. Or not only bimetal, you can have multiple layers. So isotropic is the simple case of this. So anyhow, let's let's program this. As a first step, what do we need to do? Well, we have a new terms, which is the alpha. Alpha have to be transformed from on axis to off axis. Let's first define a alpha. So in material database, say X and X prime, and Y and Y prime, and S, you define, and also a alpha X and alpha Y. No shear terms. So we can have one, two, oops. So we have a 11 and 12. So since it's a material property, let's call from here, adding here. So let's say alpha X and alpha Y. And oops. Material database is the, sometimes we have a limited material database up to here. How to extend it? We need to go to here and materials, DB, and simply extend it to cover up to M. Okay, so now we have this much material database, and we can have a, let's give us some value here. Since we are using material 4, and material 4 is the T700, and alpha X is about a very small value. You can say it's almost a 0. Not a 0. Let's say very small amount of the. So this is a 10 to the 6. 10 to the 6 is the usual one. 10 to the 6. So 0.01 and 10 to the minus 6. Okay. And then this guy, this one is about 30. 10 to the minus 6. Okay. So this is the alpha X and alpha Y. And this is the 12, and copy.
and paste and give a name. Okay, now we have alpha and x and alpha y. And what's the next step? Next step is to transform this one to a material, like a qxx transform to a q of x's. Now we like to transform to have a alpha 1 and alpha 2 and alpha 6. So this alpha 1, how do we transform strain? Let's just copy this one to here. And alpha 1 is the alpha x times what? What is the cosine here? Just cos. So cos and square is m square plus alpha y times sine square, right? There's no alpha s, so this is the one. And let's copy and paste. This one will be a sine and cos, and then copy, and twice of mn, 2 times cos minus, and this will be minus. Okay, so we do have this, and depending on the angle for each ply, as you can see that all the CTE will different depending on this angle. And now let's give a name this term as the alpha 1 to 6. Now this one is done, and now next one is what? Q bar alpha bar. Q bar. Well, we do have a Q bar here and alpha bar. And next one, we also need to have a delta T, right? Delta T. So let's start. Let's just define a delta T for delta T, all same. I mean, or we can apply the delta T each ply separately who are uniform. So let's say delta T, we dropped temperatures this much. Delta T, okay? Now we have a delta T, alpha, and Q bar. Now the point is how do we program this one? Well, we can okay, we can insert here. Again, this is a 3x3 and 3x1, and so these terms I will just call N1 temperatures will be a Q11 times a alp1, because we have a 3x3 and the 3x, we need to multiply. Plus, probably that's too much jump. Huh? Okay, these terms Q11, Q12, Q16 times alpha 1, alpha 2, alpha 6. And this is the Q21, or Q12, Q2, and Q26, and Q16, Q26, Q66. So the first term, okay, first term will be this multiply this. And second term will be this multiply this, right? So that's the one I'm trying to write down here. So Q12 and alpha 2 and in Q16 and alpha 6. Right? And then we need to multiply delta delta t. Each ply we have a delta t. Right? And also one thing here is what? A DZ. DZ means that we need to summations, and here delta t I and I to up to n. This is all I, and delta z means that we have all the thickness. Thickness, each ply thickness, HI, we have to multiply and we have to sum all the plies. Okay, we are entering these terms. So here, delta T multiply the thickness. What is the thickness here? Well, thickness, we can see that thickness is this one. Okay, so this one, and copy all up to here. And then, as I mentioned, this is the integration. Integration means that, let me integrate to here. External term. This is all summations of the whole terms. That is the first one. And then N2T and N6T, and very similar fashions, and this will be 1, 2, and 2, and this will be 2, 2, and 2, and this will be 2, 6, 6, and okay. And here will be 1, 6, and 1, and this will be 6, 2, and this will be 6, 6. Okay, so well, as long as the theory is clear, the programming is very straightforward. Okay, so this one is the N1, and I mean NT thermal term, and now another one will be a moment 1 thermal, moment 2 thermal, moment 6 thermal, and here only difference now is that wait a minute. Okay, these terms, okay, Q bar, alpha bar, delta T up to is the same, but there is a Z term, similar to here. When you have a Z, how did we do here? We multiply like that, right? So we that in mind, we have a multiplications here, and I will just copy here and here. Some moment exactly same, but instead of this thickness, we need to multiply this one, because this z is integrate will be z square minus z square, right? Top and bottoms. Okay, so that, and exactly same. And here we have to have these terms. So as sum, we just sum here, okay? There is a no moment, even though we have a temperatures, no moment. Why? Because these are all asymmetric. But anyhow, we do have an external load, and now we have this is the mechanical load, and this is the thermal load. And this one, where are we? Here. Okay. This one is the one. I will put this one into here. See, this NT can be on the left-hand side. This N is the mechanical load, and this NT is the left-hand side, which we just calculated. So we copy and paste, and this is the N1T, N2T, and N6, and this is a moment. So when we calculate this ABD matrix load, what is the load? Load was this mechanical load, but no, we like to add this thermal. So we give this one, and this is the, let's give a name as a thermal. And to calculate this strain, we have not only load, but also what? Thermal. Okay, so as you can see that no mechanical load, but let's say uniform temperatures. I like to copy as here. So whatever we zero, so all zero. Nothing happens. Nothing. No strain, as you can see here. This is the a strain. And strain and curvature. Nothing happens, but whenever we apply the temperature, like drop, like minus 10 degrees, as you can see that failure index will develop. Certain stresses is causing. And as you can see that everything will depends on the layup sequence. So each layup, even though same temperature, angle will cause different failure index because of geometric deformations and all the material property and force equilibrium and so on. So this is the one. Okay, so now we are ready. When you specify delta T, we can have a thermal load and we can have a strain and curvatures. Now, there's one very important step has to be done, which is, where is the OBX strain? Remember the OBX strain is the all in-plane strain and curvature and K1. This is the OBX strain. And this is the O-next strain, nothing but transform this strain and according to angles. Now, important point is that O-axis stress. What is O-axis stress? Remember these O-axis stress strain relations? O-axis strain was, O-axis stresses was this one, Q epsilon, right? Q epsilon. But now we have a alpha bar delta T. That have to be in there, alpha bar delta T. So here, instead of these terms, we need to have what? Minus alpha 1 times delta T. Just follow these equations, and these terms is often we make a mistake, but we have to be very careful to add these terms. This is the procedures. Conceptually, this is the what? Epsilon is the total strain. This is the thermal strain. So total strain minus thermal strain, what is that? This is the mechanical strain, and stiffness, that will be the stress. So this is what I emphasized, and do exactly same, and this. Okay. Well, I don't have to repeat again, but you can do 2 and 2, and this is the 6, and this is a 6, right? And this one, well, this one, okay, and this one, and 2, and 2, and this one is a 6. Okay, now this is the top and bottom ply, and you do the same. Epsilon 1. You could have a different thermal, but let's consider it as the same. So this one is the 2, and this is the K, and this is the alpha. Oops. This is the 6, K, and 6. So this will be, this way is a little bit easier. 1, 2, and 2, 2, and 2, 6. And this one, so 1, 6, and 2, 6, and 6, 6. Okay. Now this is the, let's take a look at, this is the all quasi-isotropic laminate, and ply, we have a 1 millimeter thick, total 1 millimeter thick, right? 8 plies,
and we have a no mechanical load. Let's see how much temperature would cause this material will fail. Well, it's a 0.06, 0.06. (166) drop, the material will fail due to the thermal stresses. Okay, well, imagine this is the all zero ply. I will do the exact, everything will remain the same, but just to look at this, change all ply zero, what happens? Well, something is not right. This has to be what? All zero stress, right? Zero ply, all same angle, and temperature will not affect the stresses, but there is a small bug. This guy doesn't look good. It's too high of axis. Anything wrong? Okay, this one, because we are all, cos zero, delta T, uniform, and this, okay, and zero, and curvature. Okay, here, okay. There is a bug here. This has to be, no. Oh, correct. Epsilon 2, K2, ZK1. Right, okay. There is a little bug there, but this is the exactly the procedure-wise correct. And please find some bug, okay? This is the, not my code, but anyhow, you can follow my recording, and you can. So for this case, just for the purpose of your checking, if it has all zero and temperature, then what will happen? No stresses, right? Because everything will shrink freely. So no stresses. No stresses, no failure index. Only we have a shrinkages, and same as the alpha x and alpha y delta t. Okay, that's the one you can double check. Okay, any questions with these procedures? Well, programming-wise, this is almost done. This is a tool so you can use a mechanical, thermal, and layup sequence, material properties, everything, and deformations, and also failure index is a very important one. And now, next step is to start with fiber and resin property. It's called micromechanics. Let's say let's say we always started with the ply, but we rather start with carbon fiber and resin. A resin or B resin, what will happen? So we like to predict ply strength, ply stiffness. that is called micromechanics, and very important. And that will be the next steps covers. Okay, thank you, and then see you next week.